Welcome. In this lecture in linear data analysis, we'll explore some applications of the singular value decomposition, or SVD. The main concepts for this lecture are that the left singular vectors form a basis for the data space of a given matrix. The right singular vectors are a basis for the weight space. These are the numbers that we multiply these data vectors in when we use a linear combination to create other data. The singular values are the generalized concept of eigenvalues, and eigenvalues are only present for square matrices. We'll also explore how we can approximate data. So one problem we can think of through this lecture is, what's the best basis for a data set? Well, let's generalize our idea of what data could be. Let's suppose that our data is a sound file and it's in stereo, which means that there's a left and a right channel. And if we're recording at compact disc quality, that means that there are 44,100 entries for every second of data. So in a 4.5 second or so audio clip, that means that we'll have a matrix that is composed of real numbers, and it's a very tall, very thin matrix. By that I mean it has well over 200,000 rows and 2 columns. And if these 2 columns are linearly independent, that is, if they're not multiples of each other, then this is a full rank matrix. Of course, the eigenvalues don't exist, but the singular value decomposition does. So we can write this matrix as an orthogonal matrix U times a singular value matrix sigma times the transpose of the right side. And in this case, I know that I can write U as the pertinent part is there's a way to do a very small SVD in most languages such as MATLAB that will return you just the economy version. And that would be U1 and U2, and these are really all that we would care about in our decomposition. So let's go through an example. Last year, I was listening to some classical music and I was talking to myself. This is not an unusual situation. By classical music, I mean music that was written and performed by someone who died before most of this class was born. I can visualize the 2 columns of this using sonograms. And here is the sonogram of the left channel, which is the first column of M, and here is a sonogram of the right channel. So these are not identical, but they have a fairly similar appearance. When I do the singular value decomposition, I get this sonogram, which has certain visual relationships, but if you look carefully, there are distinct differences between these. And then this second singular vector out of the SVD looks very different, and it should sound very different. So now, let's listen to the first column of M, which is the left channel of the original classical music with me talking over it. Now, let's listen to the second call of M, which is the right channel of the stereo clip. We now perform the SVD, and what we'll play is U1 times sigma 11, that is, times the first singular value. And what that does is it corrects the magnitude or the sound amplitude, and this is the first singular vector. And this is the second singular vector. This problem can be solved using linear algebra. These data are available on request so that you can do this yourself.